Visual motor coordination using Kohonen self-organizing map. This will be our topic today. There is little difference than what we have been talking on intelligent control and specifically neural control. So, we have been doing dynamic control, but today we will be learning how we can learn the inverse kinematics of a robot manipulator simply by learning. Okay. So, this is the 7th lecture on neural control. So, subjects that we will be covering today is visual motor coordination, the problem, camera calibration method, Kohonen self-organizing map, then extended Kohonen self-organizing map, simulation results and summary. So, visual motor coordination. Motion control of biological organisms are still highly superior to the current robot systems, not only due to sensory feedback, but also very improved information processing capability of human brain, and many things also is not known about how the information processing takes place in the brain. Research is going on to introduce visual feedback to the robotic system, hence the name visual motor coordination. So, what you are seeing here is a robot manipulator, is a 3-link robot manipulator. The 2 cameras are attached here, camera 1, camera 2. So, camera 1 gives the input, camera looks at the workspace and gives the information about the target point as well as the end effector point U1 and U2. This is the control algorithm, and from control algorithm gives the command what should be theta 1, theta 2, theta 3 such that the end effector reaches any point in the workspace. For example, this is my target point T and this is my end effector point P. Okay. So, the P should match T by the coordination, proper coordination theta 1, theta 2, theta 3 that has to be actuated such that the end effector finally comes to T, and this coordination takes place through visual feedback. So, just like given an object, how I go and catch it. For example, this tip, I can touch the tip in this way, I can touch the tip in this way. So, varieties of ways I can touch the, I can reach this point through visual feedback. This is called hand-eye coordination, right. So, see, the image points on the 2 camera planes are U1 and U2. We group together the UIs as one vector, that is U vector U1, U2, U3, U4. You see, although the object is in 3D, camera always gives the 2D information. So, the position of the manipulator is specified by theta 1, theta 2, theta 3. Okay. So, the 2 cameras provide visual feedback to the control algorithm and thus help in positioning the end effector to the relevant position. Okay. So, obviously, what we are interested is given U vector and the target vector T, find theta in steps such that the end point reaches the target point. This is called visual motor coordination. The system model, this is more accurate, that with what we said. This is base, which we will say first link, this is the second link, and this is third link. Okay. So, the base moment is circular, that is theta 1, and theta 2 up and down, and theta 3 also up and down, okay, in the vertical plane, and this rotates in the horizontal plane. So, if you look at the relationship, any point, say this point, its coordinate is z, x and y with respect to some main reference frame. So, this z, x, y, I mean actually this reference is in this from this point, from the base, the z, x, y, and the z, x, y is, for example, given theta 1, theta 2, theta 3, the end effector has a specific position z, x, y. So, this is my target point, sorry, end effector point. A special position is x, y and z. This x, y, z means this end effector has a position in the space, in the spatial coordinate x, y, z, and that can be correlated with theta 1, theta 2, theta 3 in this particular manner. Z is L2 sin theta 2, L2 is the length of the second link, plus L3 sin theta 3 here, which is the length of the third link sin theta 3, plus L1, L1 is the height. Okay. Similarly, x is the x position from here, because this is fixed, this does not move, this simply rotates. So, obviously, the x is r cos theta 1, r cos theta 1, where r is L2 cos theta 2 plus L3 cos theta 3 plus t, and t is this distance t. Okay, this distance is t. Similarly, theta 1 is tan inverse y upon x. So, this is the forward kinematics, that is, given theta 1, theta 2, theta 3, how do I compute the end effector position in the spatial coordinate, in the space. So, x, y, z. Now, from this equation I derive, given x, y, z, what should be theta 1, theta 2 and theta 3. This is called inverse kinematics. Okay. So, that is tan theta 1 is tan inverse y upon x. You can do some exercise, you can easily verify this. Theta 2 is cos inverse small x, where x is the solution of ax square plus bx plus c equal to 0, where a, b, c are given by this formulas, and theta 3 is sin inverse b minus L2 sin theta 2 by L3, and in this the three things that you need are is a, b and k. You see that you need here a, b and k. A is given by x square plus y square root over this, not time, this time is this, from third link the end effector has certain distance, okay, certain length from the end effector, sorry, the end effector has the end effector link length is the t. Okay. So, this is your this is forward kinematics, and this is inverse kinematics. So, there is nothing to be solved actually. Okay. So, mathematically, if I know these equations, if I know these parameters perfectly, inverse kinematics is solved. There is nothing to be done here, right. And now, we are not interested in the mathematical way of computing the inverse kinematics. What we are interested is, given a target point, how do I learn step by step based on visual feedback, that such that the error between this point and this point, this target point, the end point and target point, they match, or this target point comes to here. This is called, that is the problem that we are going to solve. So, methods, the cameras take the images of the workspace. Workspace means it takes the image of end effector, it locates where is the end effector and the target point. So, cameras gives us the information where is the end effector at the moment and where is the target point, how far or how far is target point from the end effector. Camera plane coordinates of the desired point u is to be found out for each camera using image processing. So, we exactly find out what is the target position and what is the end effector position from camera in terms of some vectorial quantity u. The main task is to relate them to exact workspace position, world coordinate and joint angles. So, that is, given this camera input, camera input means what? Camera gives you an image, and in image the where is the object you get in terms of some pixels, right. So, given that information, how do I correlate this information to the actual theta 1, theta 2, theta 3 such that the robot manipulator end effector finally reaches the target point. So, these relationships can be found out using model based, model free and hybrid approach. Model based method, here we derive the combined model of camera and manipulator that can be used to compute the joint space coordinate given the camera coordinate. Merit, with proper modeling it can give good result. Demerit, loss of accuracy due to camera orientation and calibration errors. So, model based means what we do, we involve the camera, the camera gives us the position. So, the earlier the models that we showed you, this model is intertwined with the model of the camera, and then we again go backward, given the camera input, what should be the theta 1, theta 2, theta 3. Okay. So, this is the back calculation. So, what is normally done, calibration of camera means we take the known x, y, z points and from there we see what are the camera output. We correlate them in terms of certain parameters, identify those parameters, and then inverse computing gives us from camera plane to XYZ plane. So, this is called model based method. So, with proper modeling it can give good result, but loss of accuracy due to camera orientation and calibration errors. So, calibration has to be done perfectly. Model free method, here we do not assume any model of the camera output is taken simply whatever is U1 and U2, we really do not correlate that to what is XYZ, there is no need, but based on that we learn using the self organizing map, Kohonen based self organizing map, we learn how do we reach the target. It is just like hand eye coordination, that is, if my object is somewhere, how I catch it. Okay. It is based on visual, like I throw and then hold it, hold an object. So, by throwing the object up and holding it, I have the hand eye coordination, that means I am looking at the thing, I am observing the object movement and then I am trying to catch it. So, this is called visual matter coordination. You see that we really do not, when I am doing this job, I am not actually aware of any model on which I am working. Rather, this whole thing I do by learning, by practicing many times, I learn how to catch. I really do not use the model of my arm, I do not really use the model of my eye, but it is simply a learning process. This is called model free approach, this one. So, this method is highly flexible, it ignores the inherent structure of the system and training as time is consuming, demerit, right. Hybrid approach, system model is also considered here for learning. This method is highly flexible and inclusion of model reduces the error in training time. Demerit, learning always takes time. To accomplish the task of coordinate transformation, camera calibration is essential. Okay. So, what is the overall thing that I told just now is that by putting a camera in the workspace, robotic manipulation can be done using model based method where camera calibration is a necessity. Second is I do not need camera calibration and still can do the learning simply by learning mechanism. The third approach is that I can still introduce the camera calibration, do offline simulation for generating data and training, and after I have done training on the offline model, that includes the robot model as well as camera model. So, then what I am now ready is that I am almost done, but still there calibration error may be there, and the model also maybe there is some discrepancy. So, what I now do, I start with these parameters, whatever the training parameters I have already learned, and I do fine tuning in the field, that is called hybrid approach. So, combination of these two. This does not require any model, neither the model of the robot manipulator or the camera model. This requires both the model of camera as well as robot manipulator. In hybrid approach, we use the positive, we take the positive of both and make a hybrid approach. Okay. Now, before I go to calibration, I will explain to you what is world coordinate and what is image coordinate. So, world coordinate is, you see that this is my main reference plane and this is my P, my target point or end effector point. My end effector is here or my target is here where the end effector has to go. So, the world coordinate is the coordinate, spatial coordinate of this point with respect to this frame. Camera is also located in a specific frame which is XC, YC, ZC, that is camera frame. Okay. If I put camera as the reference frame, so that is XC, YC, ZC. So, the world coordinate is the coordinate of target point relative to the main reference coordinate system. So, from the figure the world coordinate of point is XW, YW, ZW. What is image coordinate? Image coordinate is this camera which is placed in this reference plane, it has a focal plane, and in this focal plane the object has a position, and that position is XU and YU. Image coordinate is the coordinate of the target point relative to the image plane of the camera system. So, this is my image plane. Okay. This image plane central point is CX, CX and CY. Okay. This is the origin of this image plane. So, from the figure the image coordinate of the point P, okay, which is here, this P, this P. So, this P is XU, YU. So, in camera calibration, images of a target known geometry is taken, for example, a cubic object. Okay. So, that is here what I will do is that I place in this reference coordinate an image, an object. So, this is a cubic object. So, from this with respect to this I know what is given this point, I know what is this point, what is this point, what is this point actually spatially. So, known points I generate in x, y, z coordinate, that is the calibration, because in what is the meaning of calibration? Calibration means once I know given this point what is x, u, y, e, I should be able to predict given this point what should be x, u and y, u. Given this point it should be x, u and y, u. This is called calibration. Okay. So, correspondence between the world coordinate of a target point and its image coordinates are obtained. Camera calibration is done using size algorithm, which you can find in IEEE Journal of Robotics and Automation in 1987, which consists of two parts. First, it estimates the camera parameters by using linear least square method. Then it uses nonlinear optimization method to minimize the error among the coordinates of target image points and predicted image points. Okay. So, I will just explain very briefly. You can actually go to this paper that I just referred to understand how the calibration is done. There are other calibration method, but I am just focusing size calibration method. So, this is my world coordinate, this is my camera coordinate. So, first I transfer, I express the camera coordinate. Okay, this is camera coordinate, which is xc, yc, zc. So, the relation between world coordinate and camera frame buffer coordinates of target point P are to be found out. So, the world coordinate xw, yw, zw, this is the world coordinate of the endpoint P of point P are related to each other. So, this P can be expressed either in this reference plane or in this reference plane. Okay. So, in this reference plane, this is xc, yc, zc, and in this reference plane, this is xw, yw, zw. So, the point P here is either xw, yw, zw in world coordinate or xc, yc, zc in camera coordinate. Okay. If I assume that wherever the camera is spatially located, that to be the origin. Okay. But that this in camera coordinate xc, yc, zc can be written very simply, that is by a rotational matrix R, which is R1, R2, R3, R4, R5, R6, R7, R8, R9, because this is a 3 link manipulator. So, plus the translational term Tx, Ty, Tz, okay, where R is the rotational matrix stating camera orientation and Tx, Ty, Z is translational distance of the camera in world coordinates. Okay. So, so by using this, so how many parameters I need to compute xc, yc, zc given xw, yw, zw is actually, this is 9 plus 3, 12 parameters I need to convert from xw, yw, zw to xc, yc, zc, right. So, from world coordinate the representation of P to the camera frame coordinate of P. Now, once I have this P represented in xc, yc, zc, then there is a very easy relationship between how this P will be mapped to the focal plane of the camera. So, that is given by xu, yu is this, f is the effective focal length of the pinhole camera into xc by zc is the xu, and yu is f into yc upon zc. Alright. The perspective projection relates the camera coordinates to undistorted sensor plane coordinate as in this formula. Okay. That is a simple formula. Considering, but normally we do not observe xu and yu. What we observe is xd and yd due to distortion, which is, this distortion is due to geometric lens distortion. So, instead of xu, yu we get xd and yd, that includes the distortion. So, given xd and yd I must know what is xu and yu, and that xu and yu are given by this relationship where k1 is the coefficient of radial lens distortion, right. So, now once xd and yd is given that I am observing. So, the camera frame buffer coordinates, which is xf and yf, this is I actually get from a computer image xf and yf. Given an object, what is the position of object is denoted by xf and yf, okay, which is written by dx inverse xd sx plus cx, dy inverse yd plus cy, where Cx, Cy are the coordinates in pixels of the intersection of z axis and camera sensor plane. Dx, dy are the effective center to center distance between the camera sensor element in the xc and yc direction, and Sx is the scaling factor to compensate for the uncertainties. So, by this method finally we get xf and yf. The camera parameters are grouped into two categories. One is extrinsic parameter, which is r, tx, ty and tz. That was we said in this r, tx, ty, tz, and r is this matrix. And intrinsic parameters are f, k1, cx, cy, dx, dy and sx. So, you saw here we have the parameters associated with f. These are all computed already, this kappa 1 and rho is x d square plus y d square is the rho. So, that is already known, that is all. So, in this kappa 1 and f is there, and in this is dx, dy, sx, and also cx, cy, which we said cx and cy, and you know that cx and cy are this point is cx and cy. So, these parameters can be found out using size camera calibration method. Okay. This is the long list, I will not details. What I am trying to tell you is that simplification we can do to write xf is sx f xc zc plus cx, and yf is f yc zc plus cy, ignoring the distortion. I can write this, and once I write this, we can now represent xu dash as xf minus cx, yu dash yf minus cf. You know that I know what is yf. Okay. Similarly, xu dash upon f is sx upon xc upon zc, and yu dash upon f is yc upon zc, that is before this from this relationship. Okay. So, finally, we get these two equations. Okay. So, if I solve these two equations, I get this equation, and you see that this is simply the objective is that how I identify the camera model parameters, that we started with the world coordinate, went to the camera coordinates, from camera coordinates camera image plane, from camera image plane to the actual position of the target point in the camera image plane, which is xf and yf. So, given xf and yf and given actual xyz in the world coordinate, how do I compute these parameters, which is xx r1, sx r2, sx r3, sx tx, and then r4, r5, r6 and t1. So, these are the parameters. So, you see that I already know what is xw, yu dash, yw, because xf is known, cx and cy are given. Okay. So, xu dash is known from so these xw, yw, zw, these are all given. We can collect this data point. So, we can collect, so 1, 2, 3, 4, 5, 6, 7, 8. So, 8 data points, 8 unknowns are here. Of course, here you see the 2 unknowns are clubbed together, 2 unknowns are clubbed together, 2 unknowns are clubbed together. So, but these 8 unknowns and these are known, I can, if I have many points, I can always solve this using least square technique. So, that is what. So, this is a homogeneous equation of 8 unknowns. So, hence Sx r1, Sx r2, Sx r3, Sx tx, r4, r5, r6 and ty, they can be easily estimated. Okay. Taking one unknown value, say ty equal to 1, this equation can be solved with 7 or more than 7 event points using least square methods. Okay. Now, the other points, given these combined values, how do I estimate Sx first, and once I estimate Sx, how can I then I can easily estimate what is R1, R2, R3. Okay. So, this is a simple method. So, the first from out of the 8 unknowns, we directly get R4, R5, R6 and Ty. We have the information R1 square, R2 square plus R3 square is 1. So, also R4 square plus R5 square plus R6 square is also 1. Now, assuming, because when we estimate using least square, we do not get exact values. So, assuming 1 upon R4 square plus R5 square plus R6 square to be C, this root over, and also C upon Sx is this quantity, which you can easily see, assuming that this quantity root over R4 square plus R5 square plus R6 square estimated is equal to R1 square plus R2 square plus R3 square. So, here the assumption is R4 dash square, R5 dash square plus R6 dash square is R1 dash square, R2 dash square, R3 dash square is C. By assuming that, what we can now do is that just we have the estimate of this, which is C. We know the estimate of this. So, from there we know we can compute what is C, and we also have estimate of this. So, we know this quantity. So, we can easily find out what is Sx, right. So, with the value of Sx, the parameter R1, R2, R3 and Tx can be found out. Then the next is R7, R8, R9. They are found out because they are cross product of the first 2 rows of R, which are R1, R2, R3 and R4, R5, R6. Okay. So, finally, the nonlinear optimization used to fine tune whatever the estimation has been done, because the estimation has certain approximation, because distortion has been omitted during the estimation. So, for that a nonlinear optimization method is done. So, you say that what is the object, how the approach is xw, yw, zw. So, these are my actual points in the space coordinate, and this is my actual image coordinate xf and yf. So, this I collect from the actual system. So, like that, and then using the algorithm you can find out what is Tx, Ty, Tz, Rx, Ry, Rz, okay, and R is this rotational matrix Sx, Cx, Cy, F kappa 1, Tf by F, Tz by F. So, all these things, all the parameters of the camera can be computed using this algorithm. So, what I just told you, that camera calibration helps us to find out the camera model, that so that given x, y, z in the actual world coordinate, camera model helps me to find out what should be xf and yf, or which we say u1 and u2. Okay. Now, once I know this camera calibration, the advantage is that I really do not have to do experiment to compute. Once I do the camera calibration, I can take this model, incorporate in my robot manipulator, combine with the robot manipulator model, I can generate data. That is, given x, y, z, I can randomly generate theta 1, theta 2, theta 3. It will take to specific x, y, x, z, and that from that x, y, x, z, x, y, z, I can convert what should be my camera plane coordinates. Now we will talk about what is self-organizing map, that we have already studied in the last class, earlier. The SOM is motivated by feature of human brain. Neurons are organized in one or multidimensional lattice. The neurons compete among themselves to be activated according to a competitive learning scheme. In Kohonen, who introduced a novel neighborhood concept where the topology of input data space can be learned through self-organizing map, In this scheme, a neural lattice can be one or multidimensional. A neighborhood concept among individual neurons in a lattice is a priori embodied. As neurons update their weights upon computation, a meaningful coordinate system for different input feature over the lattice is developed. So, that is, given a neural lattice, like this is a 2-dimensional lattice, okay, and given the input space, like for example, if my input data also is coming from a geometry of a 2D, a specific 2D geometry, then the reference, the coordinate points of these neurons would be such that they would represent almost, or they will learn the actual topology of the input space. Okay. So, if the input space is 3D, they will also learn the 3D topology. If input space is 1D, they will also learn 1D topology. Okay. So, the objective of a 2D Kohonen lattice, the way it works, that this is my input data that excites all the neuron. One of the neurons gets becomes the winner. The winner is decided by the Euclidean distance between the target, the neuron reference vector and the input vector. Okay. Then each neuron is associated with the weight vector Wy. A specific neuron wins based on SOM distance measure. This is a Euclidean distance measure. Okay. The SOM learning algorithm is that choose a random value for the initial weight vector Wj, draw a sample x from the input space, find the best matching neuron at the time step n by using the minimum Euclidean distance criterion, and then like for example, this is a 1D lattice. So, this is my winning neuron, and the neighborhood neurons, like the number, this is my neighborhood neuron, the distance is 1, and this neuron, the distance from winning neuron is 2. Okay. So, while I find the winning neuron, I also find the distance of each neuron from the winning neuron, how far they are from this winning neuron. So, given a neural lattice, we find first of all winning neuron based on the Euclidean measure distance, and then the neighborhood which is closer the distance of the neighboring neuron from the winning neuron is computed. In this case, this neuron has a distance neighbor, you can easily say that we can say this is 1, and from here to here this is 2, from 8 to 3 of course would be 5. Okay. Now, because yeah, and if I think that 1 and 8 are connected, then you have to see that this distance is, the lesser distance has to be taken. Now, if I have a 2D lattice, if this is my winning neuron, then this neuron has a distance, you can easily see this neuron has a position 4 and 2, okay, and the winning neuron position is 2 and 3. So, the distance is 4 minus 2 whole square and 2 minus 3 whole square, which is 5. Okay. Of course, you can also take the square root, that is all right, whatever the distance you say. So, given that distance, we define a neighborhood function Hji. So, Hji is a neighborhood function, that means it says how close a specific neuron to a winning neuron. So, that is e to the power minus the distance square upon 2 sigma square. So, it is better that we have written distance. So, this is like this. Okay. So, e to the power minus distance square upon 2 sigma square. So, once I find out the winning neuron and the neighboring neurons with their neighborhood function, then the weights of each neuron is computed by this. This is my Kohonen algorithm, that is each neuronal index is updated based on its old reference vector. This is the learning rate, this is the neighborhood function. You know that this neighborhood function will be 1 for the winning neuron and will gradually decrease for the neurons that are farther away from the winning neuron into this is the input vector that excites the neurons minus the reference vector of the neuron. So, we will be now talking about that is Kohonen lattice self-organizing map. Now, we will be talking about extended Kohonen SOM. Okay. So, the visual feedback is used for training of the network. So, here the concept is a little different. The concept is what now given we try to correlate between input space and output space. You said in a visual motor coordinate my input space is u1, u2 camera 1 coordinate and u3, u4 is the camera 2 coordinate. So, this is camera 1 and this is camera 2. So, in that space objects are located, right, I get those points. So, this is my input space and then my output space is theta 1, theta 2 and theta 3. So, one is that we do the clustering of the input space. What is meaning of clustering of the input space? That I represent my input space using finite number of representative points, which I said that is what the Kohonen lattice does. So, in a sense what I do is that in the input space I represent some finite cells. These are finite cells, okay, which we say here in this case Kohonen neuron, and within each neuron we try to establish a relationship between the input space to the output space. Okay, that is the object. This is why we see the only Kohonen self organizing map is simply clustering. Extended Kohonen SOM is connecting this clustering to the output space. And how do we do it? So, you know that the relationship between the input space, the camera image plane coordinate to theta is actually nonlinear, but this we can assume to be linear in the discretized cell. That is the objective. So, this is what is done here, that this is my 3D lattice, this is my u1 camera 1 coordinate, camera 2 coordinate, each coordinate gives you xf and yf, xf and yf. So, you have this vector is 4 dimensional vector. So, obviously, the wi's of these neuron the 3D lattice, this is a 3D lattice and this each neuron will have a reference vector which has also the dimension 4 by 1, okay. And then we transfer or we map the input space to output space through a Jacobian matrix A by this relationship using Taylor series first order expansion, that is theta equal to theta r plus A r u minus W r. Okay. So, W r is associated reference vector, A r is the Jacobian. So, that means what I am saying is that if this is my input space and this is my rth discrete cell, for each discrete cell is associated, the discrete cell is actually a Kohonen lattice neuron, and this neuron is associated with a weight vector W r and a Jacobian vector A r as well as a reference theta vector theta r, okay. And theta given any point close to this point W r, given any other point u which is close to W r, then the corresponding theta is computed by this linear equation. But unfortunately, we do not have the information what is theta r what is AR, and WR we have learnt using the Kohonen sum. We know only U, we have to compute what is theta. So, we do not know what is theta and AR, that has to be learnt. So, this is learnt using some feedback mechanism. Okay. So, this I have already told you how theta is related to the to parameter W mu and theta mu. Okay. So, the winner neuron is selected based on the Euclidean distance first. Theta is the collective output of the winner and its neighboring neurons. So, what is final theta? Okay. So, each neuron will predict, given U1 U2, winning neuron will predict some theta, so also the neighboring neuron. So, but final theta is the overall decision making, but that overall decision making is made by giving less importance to those neuronal decision which are further from the winning neuron. Okay. So, this is my theta output, the collective output. So, this is my individual output, this is my neighborhood function of that individual neuron, and I sum that with over R. R means R is representative of a neuron. So, if my neural lattice has 100 neurons, so over 100 neurons I compute all the responses, and S inverse is simply the summation of the distance function. Okay. This is my distance function or neighborhood function. Neighborhood function, and this neighborhood function is the highest value is maximum value is 1 and all other values are less than 1. So, what is the objective? What is done is that given this target, in the beginning some kind of random theta 1, theta 2, theta 3 are generated, because we start from no knowledge. Okay. And then slowly the objective of learning is such that the end effectors should go to positions like from V0 to V1 until it reaches U target. That is the purpose of learning. Okay. So, I just learn, and this never happens systematically, randomly. I will show you a movie that would say how this actually happens. Okay. This is the learning scheme that has been using stochastic. This learning scheme has been derived by stochastic gradient descent. Okay. So, that minimizes the error between the target point and the end point. So, this is my how I learn the Jacobian matrix, how I learn my theta r. Okay. So, this is what is my final learning algorithm. My reference vector is learnt by this function, that is you can easily see this is my Kohonen learning algorithm. Theta r by this expression, where delta theta r is given by this expression, and AR is given by this expression, where delta AR is given by this expression. Okay. Where delta V is given Vn1 by V0. Okay. V0 is the you give initial theta 1, theta 2, theta 3 to the camera point, then V0, and like that in n steps whatever is the output is Vn1 in n1 steps. Okay. So, that is my delta V. Okay. So, giving this algorithm, now we try to learn a circle. We made the robot to track a circle. So, you see that this is a circle and the desired one is in blue, and the obtained the actual points that were covered by the robot manipulator is the green, and you can easily see that almost very closely followed. So, error point you see this is in the domain of 10 to the power minus 4. Okay. So, the error is very small. So, tracking of a circular path, and in this figure error in tracking. Okay. So, in this lecture the following topics have been discussed: foundation of visual motor coordination, various issues on the camera calibration, extended Kohonen self-organizing map and its use in the visual motor coordination. The references are one of our papers in IEEE Control System magazine in 1999. For camera calibration you can follow Sai paper in 1987 IEEE Journal Robotics and Automation. Also we have another paper regarding this work on intelligent system symposium. It's an international symposium on intelligent control, Munich, Germany 2006. So finally I end this lecture showing you two movie files that will show you how the self-organization of the input space take place, and finally how robot really learns through steps reaching the target point. Thank you.